Welcome to week 8 of our CAD class. This week we're going to be continuing a project that we started last week, which was the pneumatic joint project. We're getting towards the end here. Just one more project after this one. We're gonna finish up this one um, this week, and then next week we're going to start our last project, which will take us through to the end of the class. So just a little bit of refresher. Last week we did a layout sketch and we modeled all of the individual parts for this joint. This week we're going to put these parts in an assembly, and then we're going to bring in all of the COTS components, the air cylinder, all the fasteners, the pins and everything. So let's jump into it here. So the first thing we're going to do is we are going to get our cylinders imported. So we're going to open up mcmaster.com. We're going to go to air cylinders and double acting round body, stroke length of 4 inches and 3/4. And I'm going to double check in our layout sketch that that is actually correct. Yes. Okay. All right, and then we want the universal mount cylinder. And I'm actually going to scroll down real quick and open that in a new tab because we're going to need the clevis as well. All right, so what we're going to do is we're going to, really any of these formats will work, but I'm going to click this drop down and click step, hit download, and then I am going to download this one as well. All right, and then if we go over to our Onshape document here, we just click the plus and hit import. I believe you guys can't see this file dialog that pops up just because of my recording settings, but basically browse to your downloads folder in the dialog that pops up, select, we're going to start with the air cylinder and just hit open, and then this dialog will pop up. We're going to combine into a single part studio, and we're going to import with the y-axis up. Wait for that to go, and then while we're waiting on that, we can actually do another one. Gonna hit import. This file dialog will pop up again. Browse to wherever you downloaded the clevis and hit open. Then this dialog pops back up, and we need to pick the same options here. All right. So once it uploads, it has to actually like process the file, and then once it processes the file, you'll see a tab show up here on the bottom. I'm actually going to rearrange these a little bit. I'm going to put the assembly first, and then the cylinder second. Normally, if I had a lot of these files, I would create a subfolder, but I'm not going to do that right now. So I mentioned this, I believe, in our gearbox project, but I'm going to mention it again here. If you are a RoboChargers student and you are working on a project for the RoboChargers, you should not import COTS parts this way. You should not import them into your drawing or into your document that you're creating your mechanism in. We have separate documents that we put COTS parts in. The only reason that I'm importing these into the document we're using for this project is just to keep things a little neater for the CAD class. However, in season, we have documents that we put COTS parts in specifically just so we don't have multiple copies of the file. Obviously, you should check MKCAD and things like that for these components before you import them as well. However, I don't believe these cylinders are in MKCAD, and even if they are, I want to show the process of how to import a cylinder because it's a relatively complicated model. So with that being said, I'm going to leave these tabs just named what they are, just because it's got the part number in it. I mean, I guess I could clean up the name a little bit because it's a little bit long, but we'll do that later. So first of all, we're gonna hide the planes, and then what we're gonna do here is we're gonna get rid of some parts that we don't need. So the way that these models come in, they have the nut on the front and the nut on the back, and then they also have the rod shown in two positions. We need to just kind of clean this up. So what we're going to do up here is we're going to go to delete part, going to add a delete part tool feature, and then we're going to select the parts that we don't want. Whoops. Yep, there we go. Okay. And then you'll notice those parts disappear from this list over here as well. So the way that I'm going to do this, I'm going to set the body to aluminum, even though it's part stainless steel and part aluminum. It's modeled mostly solid, so just setting it to aluminum will give you a more accurate weight. If you've got the cylinder handy, you can weigh it and then figure out what the actual weight is. Okay, and then I'm going to do 300 series stainless steel for the rod. Set the appearance to light gray there. Oops. Set the appearance to something, I don't know, a little darker for the rod maybe. Okay, and then that's basically the first step. And then what we need to do next is, I'm actually going to set this to, just to make this look nice. I'm going to add an appearance just to this face and set it to one shade darker. It looks a little more realistic. Okay, that's purely for aesthetics. All right, so then the next thing we're going to do here is we are going to create what's called a composite part. A composite part is essentially Onshape's version of a multi-body part in other CAD software, if you're familiar with that. In the case of Onshape, composite parts are a nice feature if you've got, especially if you've got a COTS part that has multiple components in it, but you always have to use it as a single unit. For example, there's two parts here, but like you can't take the rod out of the cylinder. It's an inseparable unit. But it's really annoying to deal with the rod as a separate part in an assembly. You'd rather just drop it in and have it not move. Now, the way that I and most other people in FRC handle air cylinders in CAD is we just put the rod in the CAD in the retracted position, and then the only thing that moves is the clevis. Constraining the model to make the rod move is generally more trouble than it's worth, and so most people don't do it. I would recommend that everybody watching this tutorial do the same. So what we're going to do here is we're going to go up and we're going to add a composite part feature. We basically just select the parts that we want to group together in the composite part, and then once we've done that, you can see another folder shows up down here, and we get another composite part. Now what I'm going to do is I'm going to rename this. I'm actually going to rename this and just copy paste this part number, and I'm just going to rename this a little nicer name, something that's a little more neat and organized that fits kind of in on your screen easily. And I'm actually going to rename this tab the same thing. It just keeps things a little nice. You know what the part number is and you know where you buy it from, but you don't have to worry about it running off the edge of the screen. Okay, so let's go over here. We're basically going to do the same thing for the clevis. We're going to hide the planes. We're going to do it was right there. Delete part. We're going to delete the pin and the two clips. We're not going to use those. We are going to leave the nut in here though. Okay. And then both of these are, they're just carbon steel, and then they're actually zinc plated. And then we'll just set them to be, I don't know, that color. Okay, and then we're going to do the same thing where we're going to do a composite part. We're going to select both of these, and then going to give them a little nicer name. Okay. Copy that, rename the tab. All right, so that gives us the start that we need. And like I said, normally these files would be put in a standard COTS document that's somewhere else in the RoboChargers team, and then you would not you would just import them into the assembly instead of them being in the same document. So, for example, this clevis is already in that document. You would not need to download it. Next year when we go to design our robot, we don't need to download this clevis because this clevis is a pretty standard part that we've used before, and so it's already in our library. All right, so let's jump over here and let's work on our assembly. So what we're going to start with is we're going to start with I think we're going to start with all of these parts. So I think we're done with the layout sketch, so I'm going to go ahead and hide the layout sketch, and then we're going to go over to our assembly here, and we're going to go to Insert, and we are just going to select the entire components Part Studio, and then just click OK. Now, these are obviously all these parts are just floating in space. If we move them, they will wander away from their positions. Now, what we want is we want this assembly to actually move. So basically, what we need to do here is we need to make sure that we constrain things in a certain way where basically we get the motion that we want. However, all of the geometry is still constrained relative to the geometry it's related to in a way that preserves the nice relationships that we've created here in this Part Studio. So basically what I mean by that is that, all these parts here on the base, like this bracket, the tube, the spacer, this bracket here, all of these don't move in relation to each other, and we've positioned them properly in the Part Studio. So I don't want to use mates in the assembly to constrain these parts to each other because they're already in the correct locations relative to each other as defined by the Part Studio. So if we go in here and add a bunch of mates to it, like mate holes together, and then we change something over here in the Part Studio, it won't necessarily update properly, right? If we move this bracket in, but in the assembly it's still constrained to the hole on the end, for example, then if we change it here in the Part Studio, it's not going to update in the assembly. And so we want to avoid that. So the way that we're going to do this is we're going to make as much use of the group feature as we can. However, we have to be a little careful how we group things because only things that move together can be grouped. So what we're going to do is we're going to start off with this tube here, and we're going to fix it so that it can't move. That's going to form the basis of our assembly. And then what we're going to do is we're going to grab the group feature, we're going to select the tube, and everything that is attached to the tube, basically. Let's see, they've got some small parts in here. So we've got the bushing. The bushing moves with the arm here, so only the pin in the middle doesn't move. So we're going to select that as well, and then we're going to click OK. Now, the next thing that we need to do is we need to take care of these items here. Now, just grouping them together is not quite going to be enough. We have to group them to each other, but then we still have to find a way to create the joint. And this is where we're going to have to make a compromise because there's no way to make that joint and preserve the exact relationship from the Part Studio of the location of this joint here. We're going to have to just do a single mate that handles that relationship. So what we're going to do here, I'm going to get the group, we're going to grab this plate, and then grab the bushing as well. Now, if I grab this and I drag it, obviously, this wanders off, basically, which is not exactly what we want. So we can solve this easily with a mate. However, we need to be a little careful how we do the mate so that if we were to make changes over in our Part Studio, this is as robust of a joint as possible. Now, what I would like to do is do a mate from the center of this kind of pivot hole back here, right in the center of the tube, to the center of this this pin here, because if you guys remember in our assembly, should do the other side. There's a little gap here, so I can't just constrain the bushing. I can't just mate the bushing to the inside of this plate. And I also don't want to just manually put this gap in here, because if I were to go in here and change the thickness of the sheet metal or something, that gap would change, and I don't want to have to remember to go into my assembly and change a number. So there's a couple of different ways to do this. I believe we modeled this. We did. So we modeled this with um, the right plane in the middle of our tubes, which was intentional. Modeling it so that these planes are kind of in the middle of stuff is useful for doing basically exactly what we're about to do. So what I'm going to do is I'm going to temporarily hide this part as well, I guess. And I'm going to add my own mate connector. And so what I'm going to do is I'm going to go up here. I don't see it, so I'm going to search for it. Like I've said in previous videos, I have the size of the UI increased just so it captures better on video. Okay, so what I'm going to do is this guy here is going to be the origin entity. If it'll let me select it. There it goes. And did it select the right tube? Yeah, it did. Okay. And then what we need to do is move. Yeah, actually, we want to do this. Between entity. I'm not sure if it's the other side. Yes. Okay. There we go. That works too. So I guess I didn't need the plane at all. All right. Anyways, so essentially, this is a mate connector that is in between this face and this face, which is exactly in the middle, and it is aligned to this hole in here, and it belongs to this part. That's also kind of important, because whenever you insert a part studio into an assembly, like which part is this mate connector attached to, you have to specify that. So that's essentially how you make a custom mate connector. Then we click OK, and you can see the little icon here is just kind of floating in space, right? It's just kind of like drawn over top of everything, so you can always see it even if it's hidden inside of a part. Because at the moment it's actually inside this part basically, but it's drawn on top of it. So that's a little bit of a weird thing to get used to looking at it. But once we're done with this, we hide it just so it's not in our way all the time. So let's go back to the assembly here, and we can see that our mate connector shows up here as well. And so what we can do is we can do we are going to do a revolute mate. So what revolute does is it allows things to rotate, but it locks them to an axis, and it locks their position along that axis as well. So if we do revolute, we select this mate connector, and we select the middle mate connector of the cylindrical part. That's a built-in mate connector. You can always pick the middle of a cylinder. That's always a mate connector that's available to you, and it's very useful. So we click OK. It looks like that's in the right location, so let's exit out of this. And then you will notice this moves, and the bracket stays in the right location, and everything's happy. All right, so what we're going to do now is we're going to hide this mate connector. You can just right-click on it and just hit hide all mate connectors, and all the mate connectors will hide, which is usually what you want. All right, so now obviously there's a problem that we have here. So we only modeled one set of these brackets, but there's actually supposed to be there's all these same brackets on the other side. Now there's a couple of different ways of accomplishing this. So the first way of doing it, and the easiest way but the least clean way, is just to mirror all the parts in your part studio. Now that's not great because it actually creates a duplicate copy of each part, and that means that when it comes to doing exports and stuff for manufacturing, it's difficult to get a good count of the parts that you need to manufacture. So I prefer to not do that, especially on something where, something like a robot where there's a lot of parts and it's relatively complicated. If it's something very simple and I'm just trying to do it quickly, I might do that method just because it saves me time on the CAD side. and doesn't really cost me on anything on the manufacturing side. However, the best practice is to handle it in the assembly. Now, unfortunately, Onshape does not have a good mirror feature, or doesn't have a mirror feature at all in assemblies. I don't know why that is. It's very frustrating. I wish that was a feature that they had. I would assume that it's on the roadmap and will get added at some point. However, I don't have any idea when that might be. So until Onshape adds a good mirror feature like SolidWorks or an Inventor have, assemblies with symmetry is always going to be kind of a difficult thing to work with. So I'm going to show there's a couple different ways to do this. So the easiest way to handle this in the assembly is just to add the parts on the other side and then just constrain it to a hole or something, right? Just constrain it the easiest way you can. However, in our case, because we could change the length of these parts, and these hole patterns are not very robust. It's really easy to break these hole patterns in your feature tree. I really don't want to constrain these to a specific hole because that will potentially entail a lot of work down the road if I were to change the length of these tubes. So I'm going to do a slightly different method that adds more mates, however, should be a little more robust to changes in the part studio. So what I'm going to do here is I'm going to select all these parts, and I'm going to hit Control C on my keyboard to copy them, and I'm just going to paste them out here in space. And then what we're going to do is I'm going to do two kinds of mates. I'm going to do a planar mate just to attach it to the face, and then I'm going to just align up some important feature on the bracket, probably the pinhole, because that's the kind of the most important hole there is. On this bracket, I'll have to line up one of the mounting holes. Okay, so let's do this. I can just pick the center of this face. Won't let me select for some reason. Now select it twice. Cool. And then I'm just going to select this mate connector here, and it's going to be in some random location, but it doesn't matter. Now I'm going to go through, I'm going to do this for all of the parts. So middle face, and this one needs to be probably that mate connector there. And then this guy can be that mate connector there. And then this one can be, actually for this part, this part, I'm going to do something a little different. For this part, because this whole pattern here and this whole pattern here, these whole patterns are probably less likely to change than the tube, and I don't really have anything else to constrain to. I'm actually going to just do a fastened mate between this hole and that. And then this is planar mated to this face here, so all I need to do is just take care of the alignment with this hole. So what we're going to do here is I'm going to do a slider mate. Now a slider mate aligns things on an axis, and it aligns rotation on that axis, but it does not align spacing, like axial position on that axis, which is what we want. So we want to attach this to there, and then we're going to hit solve. And you'll notice the brackets are clocked in the correct orientation, but they have this spacing here, and the slider mate does not constrain the spacing. So that's what we want there, and then we have to just do this to all of them. So I guess I can just do this all from one side. Up to that, solve, make sure that looks correct. And this should preserve the orientation even as we rotate this thing, but we'll test that here in a second. And then I want to make sure I'm clicking the plate in there, hit solve. And then because we fasten mated these two holes together, it pulls this spacer bracket with it and lines it up as well. Okay, so that should be good. So that's relatively robust. Like I said, if we did change this whole pattern on the plate, stuff could break, but that whole pattern is a little less likely to change because it's at the end of the at the end of the part. It could still change though, in which case you'd have to come in here and fix those mates. But it should just be this fasten mate is the only one that should break. Okay, so now if we move this, it can still move. That's well and good. By the way, this clicking and dragging movement can be a little more laggy in Onshape than it is in other CAD programs if you're used to other CAD programs. And that's just because so every time this moves, it has to solve the constraints, all the mates, has to solve all the mates in every position that you see on your screen. And that's all being done server side, as I understand it. And so there's this kind of lagginess delay where it's sending stuff to the server's processing it, and then sending back the positions of all the components. So it's not quite as smooth as it is in most CAD programs. However, it's functional. You know, it's not like you really need this to be a super kind of agile motion. You just need to be able to move it around and check clearances and things with other parts. And so it accomplishes kind of the minimum required functionality there. Okay, so then the next thing we're going to do is we're going to bring in our air cylinder. So let's see, what's the best way to do this? Okay, so in order to constrain the air cylinder, we need to have pins. We need to have pins in place that allow us to kind of position the air cylinder where the pivots are going to be. So there's basically two common ways of doing this. Well, there's actually three. So the first way of doing it is you use a cotter pin. So you stick a pin through here, and then it has a cross hole that you put a cotter pin in to keep the pin from coming out. That is not very common in FRC, typically because all of those components are steel. They can be a little heavy. It's not a particularly tight joint. It's kind of a loose joint, and so not necessarily always suitable for FRC. Also, those pins and everything are not standard hardware that a lot of teams choose to stock, and so getting those pins is an extra thing that has to be purchased in the season. They have to make sure that they bring it with them to competition and stuff. It just adds another component. So there's typically two other options that at least the RoboChargers use. One is that we use a 1/4-inch bolt as a pivot for the cylinder, or whatever size is applicable. In our case, these 3/4-inch bore cylinders, this is a 1/4-inch hole, so a 1/4-inch bolt will fit through this. And then the clevis is also 1/4 inch as well. So if you're using a bigger cylinder, that would be a bigger hole, by the way. So you could put a 1/4-inch bolt through, or you could use a 1/4-inch standoff and put screws on either side that hold the standoff in place and pivot around that. That's essentially what we're doing here. This guy here is basically a standoff, and there's a screw from either side that holds it in place. Now, the problem is that we like to use number 10 hardware for everything, and you can get number 10 standoffs that are a 1/4 inch outside diameter. However, there's a very thin wall between the threads and the outside of the standoff. So, for example, 1032's major diameter is 0.19 inches, and a 1/4 inch is 0.25, obviously. So that only leaves a total of 0.06 inches on the diameter, and that's obviously split between either side. So you leave a wall thickness of no more than 0.03 inches left over, and so that's enough to keep a structurally standoff generally. However, if it sees a lot of load, it is possible to actually fail those threads and break the standoff. And so on an application like this where you have an intake or something, personally, I generally try to avoid using that standoff kind of method with something that might see impact load like an intake would. I certainly use it in a lot of other places where the application is either just a much less a high force application, or there are methods for isolating that joint from an impact. Um, for the purposes of this example, though, we're going to do one of each. We're going to do one pivot as a joint, one pivot is a bolt, and then one pivot is a standoff, just to illustrate how each of them are done. I want to make it clear, though, that in reality, you would probably pick one or the other for both pivots, just to keep things simpler. There's no reason to do a different style of joint on both sides of the cylinder. Another thing to keep in mind is generally the screw method will be a much sloppier joint than the standoff will. The standoff will be much tighter controlled in terms of tolerance and backlash and wiggle room and things like that, whereas the bolt will have a lot more clearance. It's also a good thing to keep in mind is that pivoting around screw threads is generally a bad thing. However, in the context of FRC, most of the time you can get away with it. You just have to be careful what you're doing. So I'm going to illustrate both, but it's important to kind of evaluate what the best option is depending on where in the robot you're using this. All right, so in order to do this, we need to, these holes are made for 1032 screws. We're going to do the bolt pivot back here, and we're going to do the standoff pivot up here. So we need to make these holes back here big enough for a 1/4 inch bolt. So we're going to go into our part studio. I don't remember where this was made. I think this is in the sketch. Yes, it was. Edit that. And then I'm going to just set this hole to be 0.255. That's generally what I do when I need a really close fitting hole for some sort of like pivot like this. All right, so that was easy. All right, so now what we're going to do is we're just going to put a bolt here. And actually, we need to measure how long it needs to be. 1.16 inches is our spacing, and then we need a little more space than that. I think we'll just do a 1.5 inch bolt. It's probably sufficient. We can change the length later if we need to. So if you guys remember from our gearbox project from a couple of weeks ago, Onshape has the standard kind of library for fasteners. So we're going to just select this whole edge, and then we're going to just insert a fastener, and it's going to just automatically mate it in place for us. So I'm going to go over here to standard content, inches, button head cap screws. We need 1/4 and we need 1.5 inches long. Hardened alloy steel, black oxide, and then hit insert. Okay, we're going to hide all mate connectors. And I'm just checking over here to make sure there's enough sticking out for a nut, and it looks like there is. However, I believe there is a nut in MKCAD. Let's check here. If not, we'll have to grab it from McMaster. Let's see. Just search 1/4 nylon insert lock nut. Okay, so we're going to select that. It's going to insert it at the origin. Close the panel here. Drag this over. Fasten mate. Want this to select the center of the hole, and then this is going to go right there. Flip the direction. Good. Okay, so yeah, 1.5 inches was perfect. You want to make sure that the screw sticks through a little bit because this little ring on the inside here of the nut is the nylon locking portion. And so you want to make sure the screw sticks completely past the nut. And you want to make sure this chamfered part sticks past the nut ideally to make sure that the nylon is engaged. Now, in case you're confused, the way that you would actually install this is you would not tighten this screw down. The nylock nut will keep the screw from coming loose. If you were to tighten this screw down, it would just bend these two plates inwards, and that would be bad, obviously. So what you would actually do is you just put the screw in. You would just get it until the nylock is engaged on the nut. You just screw it in far enough to where the nut is keeping, or the nylon is keeping the nut from vibrating loose, and then that would be all the farther you'd go. And then the cylinder would be, will be on here, and then we'll actually end up adding some spacers, which we'll do later in the video. Okay, so then for this standoff, let's go to McMaster Car here. I don't need these two tabs open. Go to standoffs, inch, thread size 1032, length will be 1 inch, and we're going to do round So, okay, so it looks like you can get these in a variety of materials. Um, you can get them in stainless, you can get them in zinc-plated steel, and you can get them in aluminum. Now, aluminum is definitely the cheapest, and if you're doing really light load stuff, aluminum is okay. However, like I mentioned, I try to avoid using these because of strength issues on intakes. So aluminum would not really be suitable for this application. So I think I'm actually liking the zinc-plated steel option. It's about double the cost, but they're still, only about $2 each. So it's a relatively reasonable price. If you have a lot of these on your robot, though, these do start to add up. So it can be worth considering another option like bolts or something if you have 10 or 20 of these on your robot. In our case, it doesn't matter. This is just an example, so we're definitely going to pick the zinc plated steel option. Now, it would be kind of dumb to download this CAD model and import it just because it's such a simple part. So we're going to kind of do what we did with the bushing, where we're just going to copy this part number. We're going to create a part in our part studio, and then uh, just assign it this part number rather than importing the CAD. So what we're going to do here is we're going to go to our part studio. We might need to create a context for this, but I'm going to give this a try first. We're going to go to our shaft generator. Does this let us? Oh no, we can't use the shaft generator for this. All right, so what we're going to do is we're just going to create a sketch. Oops, not on that surface. It's up here. We're going to create a sketch. We're going to create a circle, 0.25, and then we're going to extrude that out. We're going to create a new part though, and I'm just going to do up to face over here just to make sure it's kind of related to the geometry of this tube. Once again, that's pretty good practice. And then what I'm going to do here, I'm going to show this sketch again. I'm going to use the center point for the hole. So I'm going to do a hole feature, 1032 tapped, blind, all the default lengths are okay. So I'm going to pick the sketch point here. Actually, I could do one hole on one side and then mirror it. That's what I was going to do. But in reality, this part is actually just, it's a hole all the way through. I think it's still tapped from either side, but the hole goes all the way through because it's so short. You drill at least a half an inch deep for a 1032 thread. So really it's threaded from one side into the middle and then the other side. So in CAD, I'm just going to do, instead of blind, I'm just going to do through because it's not actually making the threads anyways. So it's just representative. Okay, so I'm going to do that. And then this part here, I'm going to rename this to the McMaster car part number. Also, I realized I have these parts hidden from earlier. I wanted those to be unhid. Okay, so I'm going to right click on this, assign material, just be carbon steel, and then the appearance will be, I don't know, like that, probably. Okay, so then going back to the assembly. Now, I believe what we have to do now is we have to, I don't think we can group this because this is now moved. I guess that's okay. So we're going to insert current document components and this guy. So yeah, if we just insert it, it'll just insert at the default location. And then we don't have the opportunity to group it with these other parts. I could put this arm in a known position and then drop it in and then group it, but I think it's going to be easier if I just made it in place and be done with it. Okay. All right, so that's there. We'll add screws later. The other thing we need to do that I noticed we forgot earlier was we forgot to put the other bushing, so I'm going to copy that with Control C, and then I'm going to do a fasten mate to this hole and then flip that around. Okay, All right, so that's that. All right, so let's get our air cylinder in here now. The one thing I want to do real quick is I want to create a mate connector in the middle here. It's kind of like we did for the tube. I want to create a mate connector in the middle that's aligned with these holes. So let's do mate connector. Origin entity will be that, and we will do between entities and just pick the back face. All right, so now we've got the mate connector. Oh, also I need to make sure before I do that can I make the owner part the composite part? I cannot. All right, it has to be this guy. All right, that's fine. It'll come with the composite part still. All right, so coming back here, let's insert. Let's do this, and then this is the weird thing about composite parts is these filters up here turn it off by default. So you got to turn it on, and then I'll turn off normal parts, and then this part, this is the part studio. This is the composite part. So click that, place it in. What I'm going to do here is we're going to do a Revolute mate with this mate connector and the midpoint of the cylinder, and then idle mate connectors, and then this guy can kind of pivot around, but it can't move left or right, and it can't deviate from the center line of this this pin here. So next, what we're going to do is we're going to do the same thing. Turn on composite parts in the filter, place that in our assembly. Come on, there we go. All right, so then what we're going to do here is we're not going to do anything that constrains left to right on this because the cylinder will be held on the correct axis because this is centered on this pin over here. So what we're going to just do is do a cylindrical mate. This guy, all a cylindrical mate does is constrain something to an axis. That axis does not constrain the part along the axial direction or in rotation. It's just purely the axis of the cylinder. Come on. There we go. All right, so that is that. I'm actually gonna flip this because I want the ports to be facing this side. All right, so then if I get out of this, I can slide this left or right, and I can also rotate the cylinder. That's how a cylindrical mate works. Okay, so then what we can do here is I don't remember exactly what the spacing was that we picked out for this clevis and the air cylinder. So let's get this lined up here. Let's just do a slider mate. Actually, no, I think we're gonna do a cylindrical as well. That'll be less constraining. We don't actually want to constrain the angle of this because the other constraints are handling the angle, so I don't want to over constrain this joint. So we're going to do cylindrical there and the center of this face. It'll let me select it. Okay, and then click OK. All right, so now this joint is still able to move. Now this is what I was talking about earlier where the clevis is in line with the rod. So if you imagine that this rod is extending, this is the correct action of the air cylinder. However, like I said as well, it's really too much work to actually constrain this rod to move. For visual purposes, it's just not worth it. Now, if you wanted to do like a nice render or something of your robot, typically what I would do is I would just come into this air cylinder and change around this delete part feature or something to have the rod in the extended position just to show what the mechanism looks like in the down position. However, for functional reasons, it really doesn't matter. So you'll notice, though, this is not constraining us to anything like the actual usable range of the actual mechanism. Now, it is generally speaking, I would say, better practice to because the air cylinder is actually constraining the angular stroke of this mechanism, I would say it's better to constrain your CAD that way so that if the mechanism is limited in its positioning by the air cylinder, then your CAD should be as well. However, because of the way that this jam nut and this clevis go on this rod and the fact that you have some adjustment in or out, and we've built that into our model, It's a little bit hard to position this correctly in relation to the air cylinder. It's a little bit easier to just position this joint angularly. So I think what we're going to do is we're going to uh, we're going to play around. We're going to basically just do a limit mate on a limit like constraint on this angle, and then it'll position the air cylinder properly, just by nature of the way that we've built the geometry here. Like the fact that we know that this cylinder works here because we did it in our layout sketch means that constraining the angle here will still be correct on the air cylinder side. So let's play around here. Let's see. I think what we want to do is a parallel constraint. I'm going to try this and see what this does. I'm not actually 100% positive this is the constraint that we need. Z. Oh. That doesn't seem right to me. Let's make different selections here. So parallel. Can we do this face to, I don't know, like that? Solve real quick. And then we can do limits on the z-axis, I believe. So limits on the angle of z-axis, I think, is what we can do here. So we will need to set a minimum. We'll set minimum to 0. Maximum is either, I don't know which direction is positive. If this is positive, I think it's right-hand rule. So I believe counterclockwise is positive. So if we do 90 degrees here, we hit solve, click OK. Let's exit out of this to allow us to do it. It looks like yes. It's very, very laggy now because it has to check every time to make sure we're within angular limits. Oh, that's better. That's better. That's a lot better. Might have just been my internet, actually. Okay, so basically that handles the motion. And you'll notice we built in this little gap here. In reality, this nut would be tightened up against the clevis. To be completely honest, I don't know why McMaster's model has this gap here. It's actually really annoying. In fact, I think we can actually move. There should be a way to. Oh, it's yes, transform is what I'm looking for. Okay, transform. We can actually move this part in this part studio. Transform by line, transform by mate connectors. So we essentially do this just like a fasten mate, basically. So we select the mate connector we want to start from and the mate connector we want to go to. I think, oh, it's this one here. Oh, but we got to flip direction. Yeah, there we go. So it's essentially just a fasten mate, right? That's basically all that is. Except it's in a part studio. Okay, so then if we go back to the assembly, all right, now the nut's in the correct position, and you see this little gap here. So like, if for example we were to build this mechanism, and because the tolerance stack up in all of these parts, like the holes are slightly off by a very little bit, each hole slightly off. There's a little bit of slop in the pins, whatever. Like everything is just a little bit off. You know, we might put this whole thing together, whatever this gap is, 1/8 of an inch or something, 0.1 inches. That gap is, set to the correct gap, but this might not actually be 90 degrees. What you could do is you could just loosen the nut, spin the rod out a little bit, tighten the nut back down, and get reduce this gap effectively or increase this gap effectively to set the position of this mechanism. And so that is best practice in terms of designing these pneumatic joints, is to build in this little gap here so that you can adjust out and in. Obviously, there's not a lot of thread engagement on the inside of the clevis, but there is enough. You could back this out a little bit more, at least one turn, and you could certainly back it. You could spin it in more if you wanted to. So that is that done. So I think at this point we need to start adding some other parts here. So we've got all our pivots, we've got all our brackets, we've got all of our parts. The only things left to do are I want to put pneumatic fittings in these ports, and then I also want to add all the fasteners. We won't add rivets just because that tends to be a little bit It's too many parts, but we'll just assume rivets, and then we'll add screws where they need to be added. Okay, so let's add the fittings. Let's go to Automation Direct's website here. There's other places you can get these, but this is probably the easiest place to get the CAD from. Go to pneumatic components. We'll do these NPT push to connects. We'll do the elbows here. And then I gotta be careful what I select. I want 1/8 inch NPT, not these other 1/8 inch ones. And I gotta scroll down and I'll find the 1/4 inch tube one. 1/4 inch tube to 1/8 inch NPT fitting. Click on the part number here, and there should be step file. So if I download that, it should download. And then we go over back to my Onshape, hit the plus, hit import. Like I said before, this open dialog won't show up in the recording, but there's an open file dialog button or window. So select the file you just downloaded, hit open, single part studio, y-axis up. I actually don't know if y-axis up needs to be done here. Basically, anytime you're importing a file that you know came from SolidWorks, you should definitely click that y-axis up button or that checkbox because Onshape uses the z-axis as the up direction, but SolidWorks uses y-axis, and so the parts will come in like turned 90 degrees, and it's really annoying dealing with up not being up in a kind of intuitive way. And so all of SolidWorks' CAD models were originally made in SolidWorks, and so anything you downloaded from McMaster-Carr, you can just assume you need to check that y-axis button. But that's also true of components from Vex and Rev and AndyMark. All of those companies use SolidWorks, so you can make that assumption. However, for Automation Direct, I don't know. Although looking at this, I mean, this kind of doesn't really have an up, so I can't really tell. But okay, this comes in as one part, which is a little annoying, but means we can only set one material for the whole thing. It's mostly plastic, but this area down here is brass. So I guess we'll set it to brass. You can override the weight if you wanted it to be correct. And then we'll set the material to, oops, sorry, set the appearance to just like this color. I think, yeah, and you can see the bottom part's silver. So like you could go in here and select faces and make the part look a little nicer if you wanted to. It tends to be a lot of work though. Generally speaking, if you've got a CAD library where you're kind of maintaining the parts and you're going to be using them over and over every year, it's okay to spend the time to make the parts look correct, especially since the CAD model is going to get used for assembly. You're going to pull the CAD model up, you're going to show it to people on the team that have potentially never seen the CAD model before, and you're going to be like, here, I need to put this mechanism together, here's the bin of parts, right? And so having the CAD model have a very good visual representation of the actual real world part is actually helpful because it's easy to recognize parts by sight. So I guess that's the argument, to take the time to color the parts the way they're supposed to. So that's good enough. This part up here is also silver, but I'm not going to bother. Like I said, I set the material to brass because that's what this is. This is, I believe, nickel plated, but internally it's brass. When in doubt, like if you can't set separate materials for the whole part, like if it's got a plastic part and a brass part, when in doubt, set it to the heavier material so that you don't have CAD library models that are actually heavier in real life than their CAD. It's okay to think your robot is heavier than it is in CAD and then make it in the real world and it actually be lighter than you expected, but going the other way is very bad. You don't want to model your robot in CAD and then end up having several extra pounds of weight because of wrong materials in the CAD model or something like that. That's bad because that's how you show up to a competition and you're overweight and you don't realize it. Your I think we're back. Okay. Sorry about that. My audio cut out. Anyways, yeah, like I was saying, you don't want to get to like the last week of build season or your first competition, throw your robot on the scale for the first time and end up being overweight. Okay, so let's go back to our assembly here. Let's insert this part. We want 2 of them. No composite parts or anything here because it just comes in as one part. Now these are a little weird. The distance that these screw into the threads are a little bit ambiguous because it just depends on how much you tighten it. So I'm just going to kind of pick a number, and that is kind of a good ballpark. For 1/8 inch NPT, 3/16 of an inch is a pretty good approximation. So I'm just going to put in an offset of 0.1875. That is about right for 1/8 inch NPT. It could be a little bit, it could be screwed in a little bit farther or a little bit less, but that's pretty close. And then I'm going to orient this so that fitting is facing that way. Okay, I'm going to do the same for this fitting. This surface here is flat. I should have mentioned this on the other one. This surface in here is flat, so you can pick the edge here or this edge here, and that gives you a good reference for where the threads start. That's what I'm picking there. Let's point this the same direction. In reality, these actually swivel, so the orientation of the tube is not fixed. It can actually rotate as the cylinder operates, which is good. Okay. So that's done. All right, so we got fittings. All right, so now we just need to go through and add fasteners. So we need a screw on either side here. We've already got the screw and the nut here because we added those in order to be able to constrain the air cylinder. We need a screw here and on the other side, and then we're not going to put in rivets for all of these other locations. You could bolt these in place, of course. These holes work for 3/16 rivets or number 10 screws. However, rivets are going to be lighter. And generally, I don't put rivets in the CAD just because there's so many of them. It's a time-consuming, labor-intensive operation, and it also slows the CAD model down. So, okay, let's go through and do what we usually do here on these standard kind of like off-the-shelf things. We'll select the holes, and we can use 1/2 inch screws here, I believe. We're going through the plate, so there won't be actually a 1/2 inch of thread in the standoff, which is good. The screws won't like hit each other in the middle or anything. We could also do 3/8, but I think 1/2 inch is a little more common size. It's better to standardize on 1/2 inch than 3/8 in my experience, just because there's a lot more useful across the robot, and having as many of your fasteners on your robot be the same as possible is good. So go to Insert, Standard Content. We're still on button head screws from earlier, so we'll switch back to 1032, switch to 1/2 inch, and hit Insert. Okay, hide all mate connectors, and there we go. Okay, so the only thing we have left to do is, up to this point, I haven't really done much with part numbering. However, I kind of want to touch on it a little bit because the way that we've been modeling up to this point is not useful once you need to come and produce parts for your robot, because on an FRC robot, we could have multiple documents, and there's going to be a lot of part studios, and each of those part studios is going to have a part, 1, 2, 3, 4, 5, 6, right? Every time you have a part studio, each of your parts are going to be named this. And so, like, if I created another part studio and started modeling, I could have 2 part 2s in the same assembly, but they're different parts. And so that's really bad. Like, you should absolutely never have that, because when you go to, make drawings or export DXFs or export STLs for 3D printing or whatever, right? Whatever you're exporting in your those have a file name. Those need to be recognizable by their part number or part name, so that you don't get parts mixed up. And if you have multiple things just called part 2, that is not helpful to anyone on the team, and it's really important to avoid that. So originally in this CAD class, I was going to go over the RoboChargers part numbering system, but in reality, I think it's a little bit out of scope here. I don't think that's really aligns with the goals of the CAD class. So If you're a RoboCharger student and you want to know what the part numbering system is, I'll explain it to you. Otherwise, I'll just wait until we get into the FTC season or the FRC season to walk you through it once we're working on an actual robot. It doesn't take long to explain, and there's a document that we've written up that will be available to everybody. If you guys are outside of the RoboChargers organization, and you're watching this video, you probably have your own part numbering system. You can kind of work out whatever works best for you. If you're curious about what the RoboChargers use, I would be happy to share it. Just post a comment below on this video, or ask me, DM me on Chief, or ask in the thread for this class or whatever, and I will be happy to share some information with you. The RoboChargers part numbering system is kind of an ongoing thing. We're kind of refining it every year. We adjust it slightly to make it work better for our purposes. The switch to Onshape definitely kind of ruffled the way that we were using the part numbering system. And so there's still some kind of stuff that we're working through to make it work better for Onshape than it did for Inventor or SolidWorks. Okay, so that being said, we're going to just pick a really simple part numbering scheme here. I'm just going to rename this part, and I'm just going to do week. This is the week 7 and 8, but I'm just going to call it week 7 because we started this project in week 7. And I'm going to do an underscore and then a 001, and then I just copy this and just rename. We're not going to rename the ones that have the McMaster part numbers because we are not manufacturing those parts. I'm just going to rename these sequentially. And then if I'm doing this and I have another part studio, what it allows me to do is basically manually make sure that I don't have overlapping part numbers. Now, a thing that I have done in the past with the RoboCharger part numbering, I take some extra measures to make sure that the numbers between all of the different part studios don't overlap. But like I said, that's really out of scope here. We only have one part studio, so this part numbering scheme is plenty good enough for what we're doing. And if we go back over to the assembly, we will see that they show up in this list with their numbers, and it's a little bit easier. If you had multiple part studios that were feeding into this, it would be much easier to tell which part is which because they're not all named. There's no overlapping names. Okay, I believe that's everything for our assembly. I'm going to do a quick once over here, make sure we didn't miss any fasteners. Oh, yes, we do have one other thing to do that I forgot to do. So let's go in here, and we need to add just some quick spacers in here. Normally we just 3D print some. So let's do that really fast. What we can do is we can create a context. We did this for our gearbox project when we created the fasteners. So we're going to do edit in context. And then what we're going to do here is go up here to spacer. And we're going to select the edge of the air cylinder and up to face there. These are going to be the same on both sides, so I'm just going to model the spacer on this side and not on the other side. And then the external diameter will be like 0.375. And we can go back in that. We can go 1/2 inch. Okay, the internal adder. So this is just going to be 1/4 inch like nominal, but I actually want this to be a bit of a loose fit on this internal diameter. So we're just going to go 0.02 on the internal diameter is probably good enough. Yeah, it depends on what your 3D printer is. If you're printing on cheaper 3D printers like Ender's, 0.02 might not be enough if they're not tuned very well. The ones that RoboChargers have, I've found, are tuned pretty good, so this is totally acceptable. If you're printing on like a Prusa, you wouldn't even need to go this much of an adder probably because they tend to print right within like 5 thou of what the actual CAD diameter is. All right, let's go up here. Let's do this again. Should be the same deal. Oops, that didn't activate. Come on, there we go. All right, so origin is here, up to face. I really wish the feature scripts remembered what your last input was. Internal adder, 0.02. Okay, and then close out of this context here. Scroll down. Let's rename these. Give these part numbers as well. That'll be part 8 and 9. And then let's select these two parts. Assign material. I'll just usually pick ABS, even though we're going to print these out of PLA because there's no PLA material. And then at the appearance, I'll set to blue because we generally use blue filament for all of our printing on RoboChargers. All right, then we go back to the assembly, and then we have to actually insert these. So for components, so for the first one, which was part 8, is this one down here. That one we can just place, and then we can edit the group, and we can just add this to the group, and then we can just copy it and constrain it on the other side. Like I said, it's good to group as many parts as possible. You don't want to be using mates for stuff that's already in the correct positions in the part studio. So we're just gonna fasten mate to this other side over here. That's good enough. That's perfect. In reality, these spacers might want to be a little bit shorter than this actual width so that they're not pinching this air cylinder. But if it, generally speaking, it's okay because we can kind of control the tension on this joint. It's okay to leave them a little bit to make them line on line, like exact dimension. Up here, it could be a little more of an issue. That being said, it's pretty easy to hit them with a file real fast when you're building the robot, just to if you need to change the thickness. And so it's not the end of the world if you make them the exact dimensions and you have to just file it down for a couple seconds during the season. However, you have something that's really important like this joint down here that you need to be nice and smooth. You know, it's a good practice to model in the gap. But for these little plastic spacers, because it's very easy to kind of sand them down by hand really fast. It's not as much of a concern. Okay, so let's insert here. Let's get this. That'll be spacer 9, and we'll just add 2 of them. And then fasten mate to, I don't know, we'll just do the inside surface here. Like that. Okay, and I believe that concludes everything that we have to do. I'm going to just give us another once over here, make sure we're not missing anything. Got our standoff in here, 2 screws, 2 bushings, fittings, air cylinder, spacers, screws. I think that's everything. Okay, and then this everything still moves just fine. Got our full range of motion. Just to confirm, if we measure from here to here, that's 0.1, and then if we extend it, we should see a 4.1 should be our dimension. And yeah, it is. So, and this, because it's a 4-inch stroke cylinder, we know that the geometry here is correct. Alrighty. Thank you guys for watching, and I will see you guys next week.